Tonight, as you settle into the comfort of your bed, you're resting in a world that appears solid, predictable, and reassuringly permanent. The pillow beneath your head feels substantial, the walls around you seem fixed and certain, and the gentle rhythm of your breathing follows the familiar patterns of everyday physics. But beneath this comforting surface of ordinary reality lies something far more mysterious and beautiful, a shimmering, probabilistic realm where the fundamental rules of existence are written in the strange language of quantum mechanics. The story of quantum physics begins not with abstract equations or incomprehensible theories, but with a simple, almost childlike question that troubled scientists at the dawn of the 20th century. Why doesn't the universe behave the way it should? For centuries, physics had been built on the solid foundation of predictability. If you knew the position and velocity of every particle in the universe, the thinking went. You could predict the future with perfect certainty. The cosmos was like a vast, intricate clockwork mechanism, each gear and spring operating according to immutable laws. But as scientists began to peer deeper into the atomic realm, they discovered something unsettling. The building blocks of reality, the electrons, protons, and photons that make up everything you can see and touch, refused to follow the comfortable rules of the larger world. Instead, they existed in a realm where certainty gave way to probability, where particles could be in multiple places at once, and where the very act of observation seemed to change the nature of reality itself. This strange behavior first revealed itself in the study of light. For centuries, scientists had debated whether light was made of particles or waves. Isaac Newton had argued for particles, tiny, discrete packets of energy that traveled in straight lines like microscopic bullets. Others, following the work of scientists like Thomas Young, demonstrated that light behaved like waves, capable of interference and diffraction, just like ripples on a pond. The debate seemed settled when experiments clearly showed light's wave-like nature. But in 1905, Albert Einstein made a startling proposal that would earn him the Nobel Prize and help launch the quantum revolution. Looking at something called the photoelectric effect, the way certain metals emit electrons when light shines on them, Einstein suggested that light must indeed come in discrete packets, which we now call photons. This created a profound puzzle. How could light be both a wave and a particle? The classical mind rebelled against such paradoxes. Something had to be either one thing or another. It couldn't be both simultaneously. But the quantum realm, as scientists were beginning to discover, operated by different rules entirely. The mystery deepened when similar wave-particle duality was discovered in matter itself. Electrons, those tiny inhabitants of atoms that we typically think of as solid particles, began to exhibit wave-like properties under certain conditions. When fired through narrow slits, electrons created interference patterns just like light waves. Yet, when scientists tried to determine which slit each electron passed through, the wave-like behavior vanished, and the electrons behaved like discrete particles once again. This phenomenon, demonstrated most famously in the double-slit experiment, revealed something profound about the nature of reality at its most fundamental level. It suggested that particles don't have definite properties, like position or momentum, until they're observed. Before measurement, they exist in what quantum physicists call a superposition of all possible states, like a coin spinning in the air that is neither heads nor tails until it lands. Imagine, if you can, what this means for the world around you. The atoms in your pillow, the molecules of air you're breathing, the photons of light that reached your eyes before you closed them. All of these exist in a constant state of quantum uncertainty. They're not quite here or there, not quite this or that, but rather shimmering in a ghostly dance of possibilities that only collapses into definite reality when the universe, in some sense, makes a measurement. This isn't just abstract philosophy. The quantum nature of reality has profound practical consequences. The electrons flowing through the device you might be using to listen to this story are governed by quantum mechanics. The chemical bonds that hold your body together exist because of quantum effects. The nuclear fusion that powers the sun, providing the warmth and light that sustains all life on Earth, depends on quantum tunneling. The strange ability of particles to pass through barriers that should, according to classical physics, be impossible to cross. As the 20th century progressed, physicists developed increasingly sophisticated ways to describe and predict quantum behavior. They created mathematical formulations that could accurately predict the probability of finding a particle in a particular state, even if they couldn't say with certainty what that state would be. They discovered that particles could become entangled with one another, creating mysterious connections that Einstein famously called spooky action at a distance. These quantum effects aren't limited to the microscopic world. In recent decades, scientists have demonstrated quantum superposition and entanglement in increasingly large objects. Molecules containing thousands of atoms have been shown to exist in superposition states. Quantum effects have been observed in biological systems, possibly playing a role in photosynthesis, bird navigation, and even the way we smell different molecules. The implications are staggering. The solid, predictable world of our everyday experience emerges from an underlying reality that is fundamentally probabilistic and uncertain. The chair you're sitting on, the air you're breathing, the thoughts flowing through your mind as you listen to these words, all of these arise from the complex interplay of quantum systems that exist in a constant state of potential, only occasionally collapsing into the definite reality we perceive. Yet rather than making the world seem cold or mechanistic, quantum physics reveals a universe that is alive with possibility. Every moment, countless quantum events are unfolding, each one a tiny act of creation, as potential becomes actual, as the ghostly shimmer of probability waves collapse into the concrete reality of our experience. As you rest here tonight, you can take comfort in knowing that you're not just lying on a bed in a room on a planet. You're floating in an ocean of quantum possibilities, supported by the mysterious forces that govern the deepest levels of reality. The very atoms of your body are engaged in an eternal dance of uncertainty and creation, connected to the larger cosmos by invisible threads of quantum entanglement. This isn't a cold, distant science, but an intimate part of your being. You are, quite literally, made of quantum mechanics. Every breath you take, every heartbeat, every gentle thought that drifts through your mind as you settle into sleep is underpinned by the strange and beautiful laws that govern the quantum realm. Tonight, as you drift toward dreams, you can rest in the knowledge that the universe itself is far more mysterious and wonderful than it appears on the surface. A shimmering tapestry of possibilities, where the impossible becomes routine, and where the very act of existing is a kind of miracle that unfolds anew with each passing moment. The dance of possibilities. As you sink deeper into the quiet comfort of evening, imagine for a moment that you could shrink down to the size of an atom and witness one of the most extraordinary phenomena in all of physics, the quantum superposition. Here, in the realm smaller than anything you can see or touch, particles perform an impossible dance, existing in multiple states simultaneously, spinning in all directions at once, occupying many positions until the universe, through the mysterious process of measurement, chooses just one reality from infinite possibilities. This isn't science fiction or philosophical speculation, it's the verified, reproducible behavior of the quantum world, a realm so strange that even the physicists who discovered it spent decades trying to convince themselves it could be real. The great Danish physicist Niels Bohr once said that anyone who isn't shocked by quantum theory hasn't understood it. And Albert Einstein spent much of his later life trying to prove that the quantum world couldn't possibly work the way it appeared to work. The concept of superposition emerged from one of the most famous thought experiments in all of science, Schrödinger's cat. Erwin Schrödinger, troubled by the implications of quantum mechanics, imagined a scenario designed to highlight what seemed to be the theory's absurd consequences. He proposed a box containing a cat, a Geiger counter, a radioactive atom, a hammer, and a flask of poison. If the atom decays, a quantum event with a 50% probability, the Geiger counter detects it, the hammer breaks the flask, the poison is released, and the cat dies. According to quantum mechanics, before anyone opens the box to look, the radioactive atom exists in a superposition of decayed and not decayed states. This means that the cat, whose fate is tied to the atom's behavior, should also exist in a superposition, simultaneously alive and dead until observed. Schrödinger intended this as a criticism of quantum theory, highlighting what he saw as its ridiculous implications when applied to the everyday world. But the quantum world, as scientists have discovered through decades of experiments, really does operate according to these seemingly impossible rules. Particles genuinely exist in superposition states, occupying multiple positions, spinning in different directions, and possessing various energies all at the same time. It's not that we don't know which state they're in. They literally exist in all possible states simultaneously. This superposition isn't a mere curiosity of physics laboratories. It's fundamental to the way the universe operates at its deepest level. The electrons in the atoms of your body exist in quantum superposition states, occupying orbital clouds around atomic nuclei, rather than following definite paths like planets around the sun. These electron clouds represent probability distributions, regions where electrons might be found if measured, but where they exist in a ghostly superposition of all possibilities until that measurement occurs. The moment a measurement is made, when a particle interacts with a detector, or when a quantum system becomes entangled with the larger environment, the superposition collapses. All the possible states that existed simultaneously suddenly resolve into a single, definite outcome. It's as if the universe makes a choice, selecting one reality from the infinite menu of possibilities. But what constitutes a measurement remains one of quantum mechanics' deepest mysteries. Does it require a conscious observer, as some interpretations suggest? Or does any interaction with the environment, conscious or not, cause the collapse? Some physicists propose that consciousness plays a fundamental role in creating reality, while others argue that the apparent collapse of superposition is simply what we observe when quantum systems become entangled with larger, more complex systems. The many worlds interpretation proposed by physicist Hugh Everett III offers perhaps the most mind-bending resolution to this puzzle. According to this view, superposition never actually collapses. Instead, every possible outcome of every quantum event occurs, but in separate, parallel universes. When you observe a quantum measurement, you're not collapsing the superposition. You're simply finding yourself in the particular branch of reality where that specific outcome occurred. In this interpretation, there are countless parallel versions of you, each experiencing slightly different outcomes of the countless quantum events occurring in your body and environment every moment. Some versions of you might have fallen asleep already, while others are still listening to these words. Some might be in slightly different moods or have made different choices earlier in the day, all because of the butterfly effect of different quantum outcomes rippling through time. While the many worlds interpretation remains controversial, it highlights just how profoundly quantum mechanics challenges our everyday understanding of reality. Whether superposition truly collapses or simply appears to from our perspective, the implications are equally stunning. The solid, definite world we experience emerges from an underlying realm of pure possibility, where the fundamental constituents of matter exist in ghostly states of potential until reality crystallizes around them. This quantum dance of possibilities isn't just academic theory. It has practical applications that are revolutionizing technology. Quantum computers exploit superposition to perform calculations that would be impossible for classical computers. While a classical computer processes information in definite bits that are either 0 or 1, quantum computers use quantum bits, or qubits, that can exist in superpositions of both 0 and 1 simultaneously. This allows quantum computers to explore many possible solutions to a problem at the same time, potentially solving certain types of calculations exponentially faster than any classical computer ever could. The development of practical quantum computers promises to revolutionize fields from cryptography to drug discovery, weather prediction to artificial intelligence. Quantum superposition also plays a crucial role in the chemical bonds that hold matter together. When atoms approach each other, their electron clouds don't simply stick together like pieces of Velcro. Instead, the electrons enter shared superposition states that span both atoms, creating molecular orbitals that exist across multiple atomic nuclei. These quantum superposition states are what allow atoms to form the complex molecules that make life possible. Even more remarkably, recent research suggests that biological systems may have evolved to exploit quantum effects. Some scientists propose that quantum superposition plays a role in photosynthesis, allowing plants to explore multiple energy pathways simultaneously and find the most efficient route for transferring energy from sunlight to chemical storage. Birds may navigate using quantum effects in specialized proteins in their eyes, creating a kind of quantum compass that helps them sense Earth's magnetic field. As you lie here in the gentle darkness, consider that your very existence depends on countless quantum superposition states. The oxygen molecules you're breathing formed through quantum chemical bonds. The neurons firing in your brain as you process these ideas operate according to quantum mechanical principles. The photons that carried visual information to your eyes before you closed them existed in superposition states as they traveled through space. You are, in a very real sense, a conscious observer emerging from the quantum dance of possibilities. Your awareness, your ability to observe and measure the world around you, may play a fundamental role in collapsing quantum superpositions and crystallizing reality from the shimmering realm of potential. Every moment of consciousness is an act of creation, selecting one specific reality from the infinite possibilities that quantum mechanics allows. This isn't to suggest that you have godlike powers over reality, but rather that you're an integral part of the universe's ongoing process of self-creation. Through your observations, measurements, and interactions with the world, you participate in the eternal dance between possibility and actuality that defines existence at its most fundamental level. Tonight, as you drift towards sleep, you can rest in the knowledge that you're not just a passive observer of a fixed reality, but an active participant in the universe's ongoing creation of itself. The quantum realm that underlies everything, from the atoms in your body to the stars in the sky, continues its dance of possibilities, even as your consciousness settles into the different kind of superposition we call dreams. The invisible threads. In the quiet of this evening, as you rest in the seeming solitude of your own thoughts and space, you are actually connected to the universe in ways that would have seemed like pure magic to scientists just a century ago. Invisible threads of correlation stretch across space and time, linking particles that may never have been in the same place, creating instantaneous connections that transcend our everyday understanding of distance and separation. This is the realm of quantum entanglement, perhaps the most mysterious and beautiful phenomenon in all of physics. The story of entanglement begins with Einstein's deep discomfort with the implications of quantum mechanics. In 1935, together with colleagues Boris Podolsky and Nathan Rosen, Einstein published a thought experiment designed to demonstrate what he saw as the incompleteness of quantum theory. They imagined two particles that had once interacted, then traveled to opposite ends of the universe. According to quantum mechanics, measuring a property of one particle would instantaneously determine the corresponding property of its distant partner, regardless of the space between them. Einstein called this spookhafte Fernwirkung, spooky action at a distance, and he was convinced it couldn't be real. How could measuring one particle instantly affect another particle millions of miles away? Such instantaneous influence would violate the cosmic speed limit set by the speed of light, contradicting Einstein's own theory of relativity. There had to be hidden variables, Einstein argued, properties that the particles possessed all along, like secret messages they carried with them as they traveled through space. But Einstein was wrong, and the universe is far stranger and more interconnected than even his revolutionary mind could accept. Over the following decades, physicists developed increasingly sophisticated experiments to test the predictions of quantum entanglement. In the 1960s, physicist John Bell formulated mathematical inequalities that could distinguish between Einstein's local hidden variable theory and the predictions of quantum mechanics. When these experiments were finally performed, starting with Alan Aspect's groundbreaking work in the 1980s, the results were unambiguous. Quantum entanglement is real. Particles can indeed become correlated in ways that transcend classical physics, creating connections that persist across arbitrary distances and operate faster than the speed of light.
But entanglement isn't quite the science fiction teleportation it might seem. It doesn't allow for faster-than-light communication or the transmission of information across space instantaneously. Instead, it creates correlations, mysterious relationships between particles that ensure their properties remain perfectly coordinated even when separated by vast distances. Imagine two coins that have become quantum entangled. While they remain connected, they exist in a superposition where each coin is simultaneously heads and tails. But here's the remarkable part. When you flip one coin and it comes up heads, the other coin, no matter how far away, will always come up tails when measured. The correlation is perfect and instantaneous, even though neither coin had a definite state before the measurement occurred. This correlation isn't the result of one coin sending a signal to the other. Instead, the two coins share what physicists call a quantum state. They are, in a very real sense, parts of a single quantum system that happens to be spread across space. The measurement doesn't trigger communication between the coins. It reveals pre-existing correlations that transcend our ordinary understanding of separate objects. The process of creating entangled particles is surprisingly common in the quantum world. When a single photon passes through certain crystals, it can split into two entangled photons that share the quantum properties of their parent. When electrons pair up in atoms or molecules, they often become entangled, their spins locked in perfect anti-correlation. Even the process of radioactive decay can create entangled particles that carry away the quantum information from the original nucleus. Once created, these entangled connections are remarkably robust, but also surprisingly fragile. The correlation persists across any distance. Entangled particles separated by hundreds of miles have maintained their mysterious connection in laboratory experiments. The record for quantum entanglement currently stands at over 1,400 kilometers, achieved using satellites to beam entangled photons between ground stations. Yet, entanglement is also delicate. Any interaction with the environment, a stray photon, a collision with another particle, even the gentle vibrations of nearby atoms can break the entanglement, causing what physicists call decoherence. The quantum connection dissolves, and the particles revert to behaving as separate, independent entities. This sensitivity to environmental interference has profound implications for our understanding of why the quantum world seems so divorced from our everyday experience. Large objects are constantly interacting with their environment, absorbing and emitting photons, colliding with air molecules, exchanging energy in countless ways. These interactions rapidly destroy any quantum coherence, causing large-scale objects to behave according to classical physics rather than quantum rules. But in carefully controlled laboratory conditions, physicists have managed to create and maintain entanglement between increasingly large and complex systems. Entire molecules containing hundreds of atoms have been entangled. Scientists have entangled clouds of millions of atoms, mechanical oscillators visible to the naked eye, and even the collective behavior of superconducting circuits. The technological applications of entanglement are beginning to transform our world. Quantum cryptography uses entangled particles to create communication channels that are theoretically impossible to hack. Any attempt to intercept the quantum information breaks the entanglement, immediately alerting the communicating parties to the presence of an eavesdropper. Quantum computers rely heavily on entanglement to achieve their remarkable computational power. By entangling many qubits together, quantum computers can explore vast numbers of possible solutions simultaneously. The more qubits that can be entangled in a coherent quantum state, the more powerful the quantum computer becomes. Perhaps most remarkably, entanglement may play a role in the structure of space-time itself. Some theoretical physicists propose that the fabric of reality, the very geometry of space and time, emerges from a vast network of quantum entanglement connecting the fundamental building blocks of matter and energy. In this view, the solid reality we experience is woven together by invisible threads of quantum correlation. Recent discoveries suggest that entanglement might even connect the microscopic quantum world to the macroscopic structures of the cosmos. Black holes, those mysterious regions where gravity becomes so strong that nothing can escape, may be connected to distant regions of space-time through quantum entanglement. Some theories propose that the information that falls into a black hole remains entangled with radiation that escapes, preserving the fundamental quantum principle that information cannot be destroyed. As you rest here in the apparent solitude of evening, consider the possibility that you are far more connected to the universe than you might imagine. The atoms in your body were forged in the hearts of ancient stars, and they may still carry traces of quantum entanglement from those stellar furnaces. The photons that brought light to your eyes today may have been entangled with other photons now scattered across the galaxy. The phenomenon of entanglement suggests that the universe is not a collection of separate, independent objects, but rather a vast, interconnected web of relationships and correlations. The boundaries between self and world, between here and there, between past and future, may be less absolute than they appear to our everyday consciousness. Some physicists and philosophers have speculated that consciousness itself might involve quantum entanglement, that the unity of conscious experience might emerge from quantum correlations between neurons in the brain. While this remains highly speculative, it raises profound questions about the nature of awareness and its relationship to the quantum foundation of reality. Even if consciousness doesn't directly involve quantum entanglement, the very fact that you can contemplate these mysterious connections makes you a remarkable phenomenon in the universe. You are a complex system of atoms and molecules that has somehow given rise to awareness, the capacity to observe, measure, and collapse quantum superpositions into definite realities. Tonight, as you prepare for sleep, you can rest in the knowledge that you are part of a universe far more interconnected and mysterious than classical physics ever imagined. The invisible threads of quantum entanglement weave through the fabric of reality, connecting distant particles in ways that transcend space and time, binding the cosmos together in a web of relationships that we are only beginning to understand. In your dreams, you may glimpse something of this deeper unity, the strange, beautiful realm where separation is an illusion and everything is connected to everything else through the invisible threads that quantum physics has revealed.
The universe's secret keeper. As you settle deeper into the gentle embrace of evening, imagine that the universe itself is keeping a profound secret. Not because it chooses to be mysterious, but because the very nature of reality makes complete knowledge impossible. This isn't a limitation of our instruments or our intelligence. It's a fundamental feature of existence itself, written into the deepest laws of physics. The universe, it seems, has built-in privacy protection that ensures some of its most intimate details will forever remain hidden from view. This cosmic secret-keeping is enshrined in one of physics' most elegant and profound principles, the Heisenberg uncertainty principle. Named after the German physicist Werner Heisenberg, who formulated it in 1927, this principle reveals that there are pairs of properties, like position and momentum, or energy and time, that cannot both be known with perfect precision simultaneously. The more accurately you determine one, the less accurately you can know the other. It's not that our measuring instruments aren't good enough. It's that the universe fundamentally forbids such complete knowledge. Heisenberg's discovery emerged from his attempt to understand what happens when we try to observe an electron. To see something, we need to bounce light off it. Photons must interact with the object and return to our eyes or detectors. But photons, even the gentlest ones, carry energy and momentum. When a photon strikes an electron to reveal its position, it inevitably disturbs the electron's motion. The very act of observation changes what we're trying to observe. Initially, Heisenberg thought this was simply a practical limitation. If only we could find a way to observe without disturbing, we could know everything about a particle. But deeper investigation revealed something far more profound. The uncertainty principle isn't about the limitations of measurement, it's about the nature of reality itself. Particles don't have definite positions and momenta simultaneously. These properties exist in a state of quantum fuzziness until the moment of observation forces the universe to choose. This principle manifests in ways that would seem magical if they weren't so thoroughly verified by experiment. Consider the simple act of trying to pin down an electron's location. If you could somehow squeeze an electron into a smaller and smaller space, making its position more and more certain, its momentum would become increasingly uncertain. Push this to the extreme. Confine the electron to an infinitely small point, and its momentum becomes completely undetermined, meaning it could be moving at any speed in any direction. This isn't just theoretical speculation. The uncertainty principle has real, observable consequences that affect the world around you. It's why atoms don't collapse. According to classical physics, the electrons orbiting atomic nuclei should spiral inward, radiating energy until they crash into the protons at the atom's center. But the uncertainty principle prevents this catastrophe. If an electron were to settle into the nucleus, its position would become very well defined, which means its momentum would become highly uncertain, so uncertain that it would have enough energy to escape the nucleus entirely. The result is that electrons exist in stable orbital clouds around atomic nuclei, maintained in their positions not by classical forces, but by the fundamental uncertainty that governs quantum systems. The chair you're sitting on, the air you're breathing, the very atoms that make up your body, all exist because the universe keeps certain secrets about the precise locations and motions of its smallest constituents. The uncertainty principle extends beyond position and momentum to other paired quantities called complementary variables. energy and time form such a pair, creating what's known as the energy-time uncertainty relation. This has profound consequences for our understanding of how the universe operates at its most fundamental level. One of the most remarkable implications involves the quantum vacuum, what we might naively think of as empty space. According to the uncertainty principle, even perfectly empty space cannot have exactly zero energy for any definite period of time. This means that the vacuum is actually seething with activity, filled with virtual particles that spontaneously appear and disappear on timescales so brief that they remain hidden from direct observation.
These virtual particles aren't merely mathematical abstractions, they have measurable effects on the real world. The Casimir effect, first predicted theoretically and later confirmed in the laboratory, demonstrates how the quantum vacuum can produce actual forces. When two metal plates are placed very close together in a vacuum, they exclude certain virtual particle wavelengths from the space between them, while allowing all wavelengths to exist outside. This creates an imbalance that pushes the plates together with a tiny but measurable force. The uncertainty principle also plays a crucial role in nuclear physics and the processes that power stars. Nuclear fusion, the reaction that makes the sun shine and creates the heavy elements necessary for life, depends on a quantum phenomenon called tunneling, which itself is a consequence of the uncertainty principle. In classical physics, protons approaching each other should be stopped by the powerful electromagnetic repulsion between their positive charges. They don't have enough energy to overcome this barrier and get close enough for the strong nuclear force to bind them together. But the uncertainty principle creates a kind of cosmic loophole. Because a proton's position is fundamentally uncertain, there's a small but non-zero probability that it can be found on the far side of the energy barrier, even if it doesn't have enough energy to classically climb over it. This quantum tunneling is what allows hydrogen nuclei to fuse into helium in the sun's core, despite temperatures and pressures that are far too low for classical fusion to occur. Without the uncertainty principle, stars would never ignite, and the universe would be a cold, dark place filled with nothing but hydrogen and helium gas. The principle also underlies many modern technologies that have transformed our world. The scanning tunneling microscope, which can image individual atoms, works by measuring the quantum tunneling of electrons between a sharp tip and a sample surface. Computer processors rely on quantum tunneling effects in their transistors. Even the simple LED lights that might be illuminating your room operate through quantum mechanical processes governed by uncertainty. Perhaps most intriguingly, some scientists propose that the uncertainty principle might be intimately connected to the nature of time itself. If the future were completely determined by the present, then in principle, perfect knowledge of a system's current state would allow perfect prediction of its future. But the uncertainty principle seems to build genuine randomness into the foundations of physics, suggesting that the future is not just unknown, but truly undetermined. This quantum indeterminacy doesn't mean that anything can happen. The probabilities are precisely calculable using the mathematical formalism of quantum mechanics. But it does suggest that reality contains an irreducible element of chance, a fundamental unpredictability that no amount of scientific progress can eliminate. Some interpretations of quantum mechanics go even further, suggesting that the uncertainty principle reflects the participatory nature of reality. The idea that the universe doesn't exist as a completely objective, observer-independent reality, but rather
emerges through the interaction between quantum systems and the process of measurement and observation. As you prepare for sleep tonight, consider that you exist in a universe that maintains its mystery not through complexity or remoteness, but through the elegant simplicity of fundamental principles like uncertainty. The atoms in your body, the thoughts in your mind, the dreams that will soon unfold, all exist within the gentle boundaries of quantum uncertainty, in a reality that preserves some secrets while revealing others. This built-in mystery isn't a flaw in the universe's design. It may be essential to its very existence. The uncertainty principle creates space for novelty, for genuine surprise, for the emergence of complexity and consciousness from simpler beginnings. It ensures that the universe remains creative, that not everything can be predicted or predetermined. Tonight, as you drift into sleep, you can rest easy, knowing that you live in a universe sophisticated enough to keep its own secrets, elegant enough to build privacy into the very foundations of reality, and mysterious enough to ensure that wonder and discovery will never end. The uncertainty principle guarantees that no matter how much we learn, the universe will always have more mysteries to offer, more secrets to gradually unveil. The impossible journey. In the gentle quiet of this evening, as you rest in what appears to be a world governed by solid barriers and impossible walls, particles throughout the universe are performing what might be the most elegant magic trick in all of physics. They are passing through barriers that should, by all classical reasoning, be completely impenetrable. Walking through walls, in a sense, as easily as you might walk through an open doorway. This phenomenon, known as quantum tunneling, is not only real, but essential to your very existence. Powering the stars, enabling the devices around you, and perhaps even playing a role in the mysterious processes of life itself. The story of quantum tunneling begins with a simple observation that troubled early quantum physicists. When they calculated how much energy particles needed to escape from atoms, or to overcome various barriers in nuclear reactions, the math consistently showed that many observed phenomena should be impossible. Particles were regularly doing things that required more energy than they possessed, crossing energy barriers as high and impenetrable as mountain ranges, yet somehow finding themselves on the other side. In the classical world, this would be like rolling a ball toward a hill and watching it mysteriously appear on the far side, without ever having enough speed to climb over the top. If you threw a tennis ball at a brick wall, you would expect it to bounce back, not to somehow materialize on the other side, with the wall remaining completely intact. Yet in the quantum realm, particles routinely perform exactly this kind of impossible journey. The solution to this puzzle lies in the wave-like nature of quantum particles and the fundamental uncertainty that governs their existence. Remember that particles don't have definite positions until they're measured. Instead, they exist as probability waves that describe where they might be found. These probability waves don't stop abruptly at barriers. Instead, they seep through walls and obstacles like water soaking through a membrane. Most of the time, when you make a measurement, you'll find a particle reflected back from the barrier, just as classical physics predicts. But there's always a small probability that the particle will be found on the far side of the barrier
having somehow tunneled through without possessing the classical energy needed to surmount it. This isn't the particle finding a hidden pathway or creating a hole in the barrier. It's a fundamental quantum mechanical process that bypasses classical energy requirements entirely. The probability of tunneling depends on several factors: the height and width of the barrier, the mass of the particle, and the quantum mechanical properties that govern the probability wave's behavior. For large objects, the tunneling probability is so vanishingly small that it might as well be zero. You will never see a person walk through a brick wall, no matter how long you wait. But for subatomic particles, particularly light ones like electrons and protons, tunneling probabilities can be significant enough to play crucial roles in physical processes. Perhaps the most important example of quantum tunneling occurs in the nuclear fusion reactions that power every star in the universe, including our own sun. For hydrogen nuclei to fuse into helium, they must get close enough for the strong nuclear force to bind them together, but they're both positively charged, so they repel each other with tremendous force as they approach. The electromagnetic barrier between them is like an enormous mountain of energy that should be impossible to cross. At the temperatures and pressures in the sun's core, about 15 million degrees Celsius and 200 billion times Earth's atmospheric pressure, hydrogen nuclei move very fast and collide with tremendous energy. Yet even under these extreme conditions, they don't have nearly enough energy to classically overcome the electromagnetic repulsion between them. If nuclear fusion depended on classical physics alone, the sun would never have ignited and we would not exist. But quantum tunneling provides a cosmic loophole. While most colliding protons bounce off each other as expected, a tiny fraction tunnel through the electromagnetic barrier and suddenly find themselves close enough for nuclear fusion to occur. This tunneling probability is extraordinarily small. Perhaps one collision in a trillion results in fusion. But the sun contains so many hydrogen nuclei colliding so frequently that even this tiny probability produces the steady nuclear burning that has sustained our star for billions of years. Without quantum tunneling, the universe would be a very different place. Stars would be cold, dark balls of hydrogen gas. There would be no nuclear fusion to create the heavier elements like carbon, oxygen and iron that make planets and life possible. The very atoms in your body, forged in the nuclear furnaces of ancient stars, exist because quantum tunneling allowed those stellar fusion reactions to proceed. Quantum tunneling also governs many processes much closer to home. The phenomenon is essential to the operation of many electronic devices that surround you. In computer processors, quantum tunneling through incredibly thin insulating layers allows electrons to flow in precisely controlled ways, enabling the rapid switching that makes digital computation possible. Some computer memory devices rely on tunneling to store and retrieve information. The scanning tunneling microscope, one of the most powerful tools in modern science, uses quantum tunneling to create images of individual atoms. A sharp metallic tip is brought very close to a surface, so close that electrons can tunnel across the tiny gap. By measuring the tunneling current as the tip scans across the surface, scientists can map the positions of individual atoms with extraordinary precision, literally seeing the quantum world atom by atom. Even more remarkably, quantum tunneling may play crucial roles in biological processes. Some researchers propose that enzymes, the molecular machines that catalyze chemical reactions in living cells, exploit quantum tunneling to function more efficiently than classical chemistry would allow. Electrons and protons may tunnel through energy barriers in enzyme-active sites, enabling biochemical reactions to proceed at the temperatures and conditions found in living organisms. There's growing evidence that quantum tunneling is involved in photosynthesis, the process by which plants convert sunlight into chemical energy. In the initial stages of photosynthesis, electrons excited by light appear to tunnel through molecular structures with remarkable efficiency, finding optimal pathways for energy transfer that would be impossible through classical means alone.
Some scientists even speculate that quantum tunneling might be involved in genetic mutations, the random changes in DNA that drive evolution. High-energy radiation or chemical damage might cause protons to tunnel between different positions in DNA bases, creating the spontaneous mutations that provide the raw material for natural selection. If this is true, then quantum tunneling would be one of the driving forces behind the evolution of life itself. The phenomenon extends beyond individual particles to more exotic quantum systems. In superconductors, materials that can conduct electricity with zero resistance, pairs of electrons tunnel through barriers that would stop individual electrons, creating the frictionless flow of electrical current that makes these materials so remarkable. Superconducting quantum interference devices, or SQUIDs, use electron pair tunneling to create sensors so sensitive they can detect magnetic fields billions of times weaker than Earth's magnetic field. Quantum tunneling also occurs in the decay of radioactive nuclei. When an atomic nucleus is unstable, particles can tunnel out of the nuclear potential well, even when they don't have enough energy to escape classically. This tunneling process determines the half-lives of radioactive elements and plays a crucial role in nuclear physics and the dating of ancient materials. Perhaps most intriguingly, some theoretical physicists propose that quantum tunneling might be involved in the creation of universes. In certain cosmological models, entire universes can tunnel into existence from quantum vacuum fluctuations, emerging from nothing through a process analogous to the particle tunneling we've been exploring. Our entire cosmos might owe its existence to the ultimate quantum tunneling event. As you prepare for sleep tonight, surrounded by the apparent solidity of the everyday world, consider that you're actually embedded in a universe where the impossible routinely becomes possible through the elegant mechanism of quantum tunneling. The fusion reactions in distant stars, the electronic devices around you, possibly even the biochemical processes that maintain your life, all depend on particles performing impossible journeys through barriers they shouldn't be able to cross. This isn't magic, despite its magical appearance. It's one of the most precisely understood and mathematically described phenomena in all of physics. The probabilities can be calculated exactly, the experimental results predicted with extraordinary accuracy. Yet, the underlying reality remains wonderfully mysterious. Particles somehow crossing barriers without classical pathways, finding themselves in forbidden regions through the sheer probability structure of quantum mechanics. Tonight, as you drift towards sleep, you can take comfort in living in a universe creative enough to provide loopholes in its own rules, elegant enough to make the impossible possible, and mysterious enough to ensure that quantum tunneling will continue to surprise and delight scientists for generations to come. The barriers that seem absolute in our everyday experience are revealed at the deepest level to be permeable membranes through which the quantum world flows with graceful impossibility.